Welcome back to our course on systems engineering. And in this lecture, which we're going to cover chapter 4 in system engineering principles and practices, we're going to be talking about system engineering management. And just for context sake, just remember that we're still working through the part 1, the foundations, and this is the last of 4 chapters that are part of that section. So we'll just get into this now. First of all, thinking about management system development and risk. So as noted in our first chapter, system engineering is an integral part of the management of a system development project. The part that system engineer plays is in the project management function is included in the next figure, and we'll see that in a minute. The ovals in the diagram represent the domains of project management and those of its principal constituents, system engineering and project planning and control. It is seen that both constituents are wholly contained within the project management domain, with technical guidance being the province of system engineering, while program finances and contractual guidance are the province of the project planning and control. The allocation of resources and definition of tasks are necessarily shared functions. To better understand the many different functions of system engineering, this chapter and this lecture describes some of the main features of the project management framework, such as the work breakdown instruction, WBS, project organization, and the system engineering management plan, SEMP. It also discusses the subject of risk management, the organization of system engineering efforts, and the capability maturity model integrated as it applies to system engineering. So this is the figure here showing the system engineering as a part of a project management. The engineering of a complex system requires the performance of a multitude of interrelated tasks by dozens or hundreds of people, management leaders, and a number of contractors or other organizational entities. These tasks include not only the entire development process, but also usually everything needed to support system operations, such as maintenance, documentation, training, and so on, which must be provided for. Test experiment facilities and transportation have to be developed and acquired. The tasks involved in project management and system engineering include planning, scheduling, cost, and configuration control need to be explicitly dealt with. The management complexity is addressed with defined roles for the management team leaders. The program management, or PM, is responsible for the overall scope of an initiative from beginning to end, overseeing multiple projects that lead to ultimate objectives that benefit the organization. The PM develops and implements the strategy for the program team, optimizing the work across projects, and maintaining the budgets and reporting the program performance to the client and senior organizational management. The long-term organizational goal, guidance, evaluation, and direction of the program. In short, the person is responsible for planning, governance, and overseeing the successful delivery of the program output/product. The project manager is in charge of a specific project in an organization, planning, budgeting, and monitoring the daily activities of the project. The role includes identifying needed resources, hiring appropriate staff, setting milestones, identifying new technologies, and mediating conflicts. The project manager is the bridge between the PM, the program manager, upper management, and the team tasked with the actual execution of the project. The system engineer, SE, is responsible for maintaining a view of the whole system product, developing and integrating all components, and evaluating performance against all contract specifications. The system engineer assists in the development of strategy and planning, conduct the technical engineering development of the system, integrates and tests all components and final system, and ensures the operation and delivery of the product. The sections in this chapter and this lecture are intended to apply to the management of systems engineering activities for all types of complex systems. However, in the management of software-intensive systems, in which essentially all of the functionality is performed by software, there are a number of special characteristics that need to be considered. These are noted in particular in a future chapter, chapter 14. And in terms of proposal development and statement of work, system development often starts with someone who has a need, a customer who requests support, often in the form of a request for proposal, RFP, when in a competitive environment. Following a corporate decision to respond to the RFP, a program manager or a professional proposal team is assigned to generate the proposal. While a system engineer may not officially be assigned to the team, it is essential that the technical concepts and implied design and interfaces are feasible. Hence, even in the early phases of a project, the integration of system engineering with project management is evident. A critical element of the proposal is the statement of work, or SOW. This is a narrative description of the work that is needed to develop the system to meet the customer needs. The system engineer concerns will focus on the product to be developed, answering the scope of work in the SOW includes all the products and services needed to complete the effort. Specifically, the system engineer focuses on being responsive to the customer needs, ensures a statement of work is based on a credible concept of operation, reviews the implied design for the use of legacy components and their availability, examines to see if the proposed system integrates commercial off-the-shelf or COTS, and to determine the technology readiness levels for the important subsystems envisioned in the preliminary system design. This early planning sets the stage for the work the technical contributors will have to live with throughout the life of the project. Let's talk about the work breakdown structure, or WBS. The successful management of the system development effort requires special techniques to ensure that the essential tasks are properly defined, assigned, scheduled, and controlled. One of the most important techniques is the schematic organization of project tasks into a form called the WBS, or less commonly the project or system breakdown structure. It defines all of the tasks in terms of goods and services to be accomplished during the project in terms of a hierarchical structure. Its formulation begins early in the concept definition phase to serve as a point of reference for concept trade-off studies. It is then more fully articulated in the latter stages to serve as a basis for the system lifecycle costing. The WBS is often a contractual requirement in competitive system developments. The WBS typically defines the whole system to be developed, products developed, produced, tested, deployed, and supported, including hardware, software, services, and data. It defines a skeleton or framework on which the project is to be implemented. So here is an illustration of the levels of a WBS, a system product breakdown structure. So elements of a typical WBS, the WBS format is generally tailored to the specific project in hand, but always follows a hierarchical tree structure designed to ensure a specific place for every significant portion of work under the project. For purposes of illustration, the following paragraph describes the main elements of a typical defense system WBS, with the system project at level 1, the hierarchy, some WBS structures begin at level 0. Keep that in mind. The level 2 categories may be broken down as the following: 1.1 system products, 1.2 system support, 1.3 system testing, 1.4 project management, and 1.5 system engineering. So then getting into the details of the WBS, the system product is the total effort required to develop, produce, and integrate the system itself together with any auxiliary equipment required for its operation. So we can be thinking about that here. The level 3 entries are seen to be several subsystems as well as the equipment required for their integration, that is assembly equipment and other auxiliary equipment used by more than one subsystem. Then if we consider the layers below that, the level 4 and 5 breakdowns of one of the subsystems into constituent components, which represents definable products of development, engineering, and production effort. It is preferred that integration and test of hardware and software components is done separately for each subsystem, and hence the tested subsystems are integrated into the final system for testing. So you can be thinking of that as 1.3 and below, as we have listed over here. Finally, the cost allocation and control purposes, each component is further broken down at level 5 into work packages that define the several steps of the component's design, development, and test. From this level and below, the WS elements are often expressed with action words. For example, purchase, design, integration, test. So for 1.2, system support or integrated logistics support provides equipment, facilities, and services necessary for the development and operation of the system product. These items can be categorized, that is level 3 categories, under 6 headings. So we're showing those 1.2.1 supply support, 1.2.2 test equipment, 1.2.3 transport and handling, 1.2.4 documentation, 1.2.5 facilities, and 1.2.6 personnel and training. Each of the system support categories applies to both the development process and system operation, which may involve quite different activities. Moving on to 1.3 system test, it begins after design of the individual components have been validated via component testing. A very significant fraction of the total test effort is usually allocated to system level testing, which involves 4 categories of test as follows. As we list here, 1.3.1, integration testing. This category supports the stepwise integration of components and subsystem to achieve a total system. 1.3.2, system testing. This category provides for overall system test and the evaluation of test results. 1.3.3, acceptance testing. This category provides for factory and installation test of delivered items, delivered systems. 1.3.4, operational testing and evaluation. This category tests the effectiveness of the entire system in a realistic operational environment. Individual tests to be performed at each level are prescribed in a series of separate test plans and procedures. However, an overall description of test objectives and content and a listing of the individual tests to be performed should be set forth in the integrated test planning and management document, the test and evaluation management plan, or TEMP, in defense acquisition terminology. Other chapters are devoted to the subject of system integration and evaluation, so we'll be getting to that later. Then for 1.4, project management tasks include all activities associated with project planning and control, including the management of the WBS, costing, scheduling, performance measurement, product reviews and reports, and associated activities. 1.5, system engineering tasks include the activities of the systems engineering staff in guiding the engineering of the system through all conceptual and engineering phases. This specifically includes activities such as requirements, analysis, trade-off studies, analysis of alternatives, technical reviews, test requirements and evaluation, system design requirements, configuration management, and so on, which are identified in the SEMP, the System Engineering Management Plan. Although an important activity is the integration of specialty engineering into early phases of the engineering effort. In other words, concurrent engineering. The WBS is structured so that every task is identified at the appropriate place within the WBS hierarchy. System engineering plays an important role in helping the project management to structure the WBS so as to achieve this objective. The use of the WBS as a project organizing framework generally begins in the concept exploration phase. In the concept definition phase, the WBS is defined in detail as a basis for organizing, costing, and scheduling. At this point, the subsystem have been defined and their constituent components defined, components identified. Also, decisions have been made, at least tentatively, regarding outside procurement of elements of the system. Accordingly, the level down to which the WBS needs to be defined in detail should have been established. It is, of course, to be expected that the details of the WBS evolve and change as the system is further engineered. However, its main outline should remain stable. Moving on with a few more considerations for cost control and estimating, the WBS is the heart of the project cost control and estimating system. Its organization is arranged so that the lowest indenture work packages correspond to cost allocation items. Thus, at the beginning of the project, the target cost is distributed among the identified work packages and is partitioned down as lower level packages are defined. Keeping track of the actual cost is essential along with the actual time required to develop a system component. Project cost control is then exercised by comparing actual reported cost against estimated cost, identifying and focusing attention on those work packages that deviate seriously from initial estimates. If any new work is required to be carried out, estimations are needed for this and see if it can be accommodated with the final amount in the budget. Time management is key to cost control, especially if project deadlines are missed, since the longer the project is dragged on, the higher the cost incurred, which effectively means that the budget will be exceeded. Another technique to cost control is to identify the value of the work that has been carried out as the project progresses, an approach commonly known as earned value. Early in the budget planning process, the program manager should conduct an affordability assessment to demonstrate that the project projected funds and manpower requirements are realistic and achievable. The activity would examine all physical demands from acquisition, development, testing, sustainment, and management, comparing the projected costs with the total budget. This is best conducted on a yearly basis, noting the funding availability, inflation, and development risk. Key participants at all levels should be engaged to ensure the best expertise and prior experience is included. Another key component for adequate cost estimating is the cost of a life cycle analysis. This approach is to determine and compare among alternatives in each development phase to acquire, develop, operate, and maintain all system elements for the most cost-effective options. Note that the least costly current element may not be a sound decision over the life of the system due to sustainment and replacement cost. Hence, the life cycle cost analysis is best conducted in an early planning and conceptual design phases of the project. The collection of project costs down to the component level and their distribution among the principal phases of project development, engineering, and fabrication is essential also for contributing to a database which is used by the organization for estimating the cost of future projects. For new components, new estimates must be developed by adapting the previous experience cost of items directly comparable to those in the projected system at the lowest level of aggregation for which cost figures are available. At higher levels, departures from one system to the next become too large to reliably use data derived from previous experience without major correction. It should not be expected that the lowest indentured level would be uniform throughout the various subsystems and their components. For example, if a subsystem is being obtained on a fixed price subcontract, it may well be appropriate to terminate the lowest indenture in the WBS at that subsystem. In general, program control includes costing, is exercised at the level at which detailed specification, interface definitions, and work assignments are available, representing in effect a contract between the project and the organization charged with the responsibility for developing, engineering, or fabricating given elements of the system. There's also the critical path method. The network scheduling techniques are often used in project management to aid in planning and control of the project. Networks are composed of events that activities needed to carry out the project. Events are equivalent to a milestone indicating when an activity starts and finishes. Activities represent the element of the work or task usually derived from the WBS that need to be accomplished. Critical path analysis is an essential project management tool that traces each major element of the system back through the engineering of its constituent parts. Estimates are made of not only the size, but also the duration of effort required for each step. The particular path that is estimated to require the longest time to complete its constituent activities is called the critical path. The differences between the time and the time required for other paths are called slack for those paths. The resulting critical path network is a direct application of the WBS. The system engineer uses CPM to understand the dependencies of task activities, help prioritize the work of the technical team, and to communicate graphically the work of the entire program. So next, let's talk about the system engineering plan and system engineering management plan. In the development of a complex system, it is essential that the customer and all of the key participants in the system's development process not only know the key system requirements and their own responsibilities, but also know how they interface with one another. Just as special documentation is required to control system interfaces, so the interfacing of responsibilities and authority within the project must also be defined and controlled. This is usually accomplished through the preparation and dissemination of the systems engineering plan, the SEP, for the governance contract, or a SEMP, which once again is a system engineering management plan. The primary responsibility of creating such a plan for guiding the engineering effort is that of the system engineering component of project management. The SEP is typically associated with product development for the US government. So USD AT&L has stated all programs responding to a capability of or requirements document, regardless of acquisition category, shall employ a robust system engineering approach that balances total system performance and total ownership costs within the family of systems of systems content. Program shall develop a system engineering plan, a SEP, for the Milestone Decision Authority, MDA, approval in conjunction with each milestone review and integrated with the acquisition strategy. This plan shall describe the program's overall technical approach, including processes, resources, metrics, and applicable performance incentives. It shall also detail the timing, conduct, and success criteria of the technical reviews. End of quote. The SEP would be uploaded as plans are modified. It would be updated as plans are modified, development progress is made, known risks are mitigated or significant changes, new risks are identified, and the technologies are adopted. The SEP government, that is the customer, technical planning expectations from their perspective. It provides contractor guidance for system engineering as applied to the acquisition program. The SEP communicates technical management approach to the program team, stakeholders, and contractor teams, and is required for milestone approval. So does one need a SEP or a SEMP? That's a question that we want to address next. A SEMP, SEMP, should be developed by the prime performing organization by the senior system engineer for all new program development. For a government contract, a SEP, SEP, is acceptable only if it addresses the overall program system engineering technical approach across the government, prime, and subcontractor domains. Typically, a SEMP, SEMP, may not flow down the system engineering process and requirements to all program subcontractors and vendors. Other possible SEP/SEMP differences include government stakeholder versus contractor perspective, problem/requirement space versus solution space, program requirements versus technical system requirements, technical strategy review focus versus what and how the systems are reviewed, and planning integrated between government and contractor versus total integration of engineering between all contributing parties. Okay, now let's think about the structure of the system engineering management plan. The importance of having and formalized plans for managing the engineering effort is by requiring the contractor to prepare a SEMP, SEMP, as part of the concept definition effort. The most important function of a SEMP is to ensure that all of the many active participants, subsystem managers, component design engineers, test engineers, system analysts, specialty engineers, subcontractors, etc., know the responsibility to one another. This is an exact analog of the component interface function of system engineering definition, defining the interactions among all parties of the system so that they fit together and operate smoothly. It also serves as a reference for the procedures that are to be followed in carrying out the numerous system engineering tasks. The places of the SEMP in the program management planning is shown in this figure that we're showing now. The SEMP is intended to be a living document, starting as an outline and being elaborated and otherwise updated as the system development process goes on. Having a formal SEMP also provides a control instrument for comparing the planned tasks with those accomplishments. Well, let's consider the elements of a typical SEMP. The SEMP contains a detailed statement of how the system engineering functions are to be carried out in the course of system development. It can be considered to consist of 3 types of activities. First, development program planning and control, which describes the system engineering tasks that must be implemented in managing the development program, including statement of work, organization, schedule, program design and test readiness review, technical performance measures or TPM, and risk management. 2, system engineering processes. They describe the systems engineering process as it applies to the development of the system, including operational requirements, functional analysis, system analysis and trade-off strategy, and system test and evaluation strategy. 3, engineering specialty integration. This describes how the area of specialty engineering are to be integrated into the primary system design and development, including reliability, maintainability, and availability, also called RMA engineering. 2, producibility engineering. 3, safety engineering, and 4, human factors engineering. A typical SEMP outline is tailored to the development system, but could include an introduction that has scope, purpose, overview, applicable documents, program planning and control, which would contain organizational structure, responsibilities, procedures, and authorities, work breakdown structure, milestone and schedules, program events, program technical test readiness reviews, technical and schedule performance metrics, engineering program integration and interface plans. And then there would be the system engineering processes, which would address mission, system overview graphic, requirements and functional analysis, trade studies, that is analysis of alternatives, technical interface analysis / planning, specification tree / specifications, model and simulation, test planning, logistics support analysis, and system engineering tools. Then finally, for engineering integration, it would contain the integration design / plans, specialty engineering, compatibility interface analysis, and producibility studies. So for the organization of system engineering, despite decades of study, there are many options, but no general agreement on which organizational form is most effective for a given type of enterprise. For this reason, the organizations participating in a system development project are likely to employ a variety of different organizational styles. Each individual style has been evolved as a result of history, experience, and personal preferences of upper management. Accordingly, despite its central importance to the success of a given system development project, the system engineering function will usually need to adapt to pre-existing organizational structure. Virtually all system development projects are managed by a single industrial company. Hence, it is the organizational form of the company that drives the organization of the system engineering. In most cases, this company will develop some subsystems in-house and contract for other subsystems with subcontractors. We will refer to the first company as a prime contractor or system contractor, and to the collection of participating contractors as a contractor team. This means that the system engineering activity must span not only a number of different disciplines, but also several independent companies. The organizational structure of the prime contractor is usually some form of a matrix organization. In a matrix organization, most of the engineering staff is organized in discipline or technology-oriented groups. Major projects are managed by project management teams reporting to a vice president for project management or equivalent. At times, these teams are called integrated product teams or IPTs. Technical staff is assigned to individual projects as required, but employees retain affiliation with their engineering groups. The main variation in matrix type organizations relate to whether the bulk of the technical staff assigned to a project is physically relocated to an area dedicated to a project and remain as full-time participants through much of the development, or whether they remain in their home group areas. A related difference is the degree to which authority for the direction of the technical work assignment is retained by their home group supervisors. As stated earlier, the organization of the system engineering function is necessarily dependent on the system contractor's organizational structure. There should be some common practice, however, and so that's something that we had in an earlier figure to be thinking about. A major system project should have a single focus of responsibility for the system engineering function, that is a project system engineer, apart from the project planning and control function. As an integral part of project management, an appropriate title might be associate or deputy project manager for system engineering, or more simply, system engineering manager. Since the system engineering function is of guidance, authority is exercised by establishing goals, that is requirements and specifications, formulating task assignments, conducting evaluations like design reviews, analysis and tests, and controlling the configuration. Effective technical communications are difficult to maintain in any organization for a variety of reasons, many of them inherent in human behavior. They are nevertheless absolutely vital to the ultimate success of the development project. Perhaps the single most important task of the project's system engineer is to establish and maintain effective communication among the many individuals and groups inside and outside the company whose work needs to interact with others. This is a human interface function corresponding to the system physical interface functions that make the system element fit together and operate as one. Since the system engineer usually works in parallel with rather than through established lines of authority, he or she must exercise extraordinary leadership to bring together those individuals who need to interact. There are several different means of communications, all of which need to be exercised as appropriate. One, all key participants need to know what they are expected to do, when and why. The what is expressed in the task statement and WBS. The when is contained in the schedule, milestones, and critical path networks. And the why should be answered in the requirements and specifications. A clear and complete statement of the why is essential to assure that the designers, analysts, and testers understand the objectives and constraints of the task assignments. Two, participants must be aware of how their portions of the systems interact with other key elements and the nature of their mutual interdependence. Such interactions, and particularly their underlying causes, can never be sufficiently covered in specification documents. The awareness can only be provided by periodic personal communication among the responsible participants and the documentation of any resulting agreement, interface definition, and so on, however small or tentative. System engineering must provide the glue that binds these items of system design through the formation of interface working groups and the development of interface control documents and such less formal communications as may be needed in special cases. Three, subcontractors and other key participants at remote sites must be integrated into the project communication framework. At the management level, this is the task of the system project manager, but at the engineering level, it is the responsibility of the project systems engineering staff. It is essential that the same two coordinating functions described above be provided for the entire contractor team. For this purpose, conventional formal contractual mechanisms never suffice and sometimes hinder. Accordingly, special effort should be made to integrate the team members effectively into the total system development effort. This needs to be carried out at the two levels: one, periodic program management reviews attended by top-level representatives of the contractor team, and two, frequent technical coordination meetings concerned with specific ongoing aspects of the program. For the principal leaders of the system design effort must have a regular and frequent means of communication with one another to keep the program closely coordinated and to react quickly to problems. This is discussed next here in the following paragraphs and just what I'm going to be sharing here. So system analysis staff. An essential part of systems engineering organization is a highly competent and experienced analytical staff. Such a staff needs not be a single entity, nor does it need to be organizationally co-located with the project staff itself, but it must be part of the systems engineering organization, at least during the concept and early engineering phases of the project. The system analysis staff must have a deep understanding of the system environment with respect both its operational and physical characteristics. In both instances, it must be able to model the system environment by use of mathematical and computer models to provide a basis for analyzing the effectiveness of system models. In the concept exploring phase, the system analysis staff is a source of much of the quantitative data involved in defining the system performance required to meet the operational requirements. In the concept definition phase, the analysis staff is responsible for constructing the system simulation used in the trade-off studies and the selection of the best system concept. Throughout the engineering development stage of the program, the analysis staff is involved in numerous component trade-off studies. It conducts test analysis to derive quantitative measures of the performance of the system prototype and contributes to defining the quantitative aspects of system design specification. While the system analysis staff must be skilled in mathematical modeling, software design, and other specialized techniques, its members are also required to have a system perspective and a thorough knowledge of the operational requirements of the system under development. Next, the system design team. The exercise of leadership and coordination in any large program requires one of the teams of key individuals working closely together, maintaining a general consensus on the conduct of the engineering program. A system design team for a complex system development project may have the following members: a system engineer, a lead subsystem engineers, software system engineers, support engineers, test engineers, customer representatives, specialty and concurrent engineers. So the customer representative is an advocate for the system requirements. The advantage of the team approach is that it generally increases the spirit de corps and motivation of the participants and broadens their understanding of the status and problem of the other related aspects of the system development. This develops a sense of ownership of the team members in the overall system rather than the limitation of responsibility that rule in many organizations. It makes response to unexpected problems and other program challenges more effective. In particular application, the leadership of the system development needs to be tailored to the prime contractor's organization and to the customer's level of involvement in the process. Most important common denominators are: one, quality of leadership of the team leader; two, representation of those with key responsibilities; three, participation of key contributors. Without energetic leadership, the members of the system design team will flounder or go their separate ways. If for some reason the person designated as the project system engineer does not have the required personnel leadership qualities, either the project engineer or a deputy system engineer should assume the team leadership role. The presence of the leaders of the major portions of the development effort is necessary to bring them into the design decision process, as well as to have them available to use their resources to resolve problems. There are usually several senior system engineers whose experience and knowledge are of great value to the project. Their presence adds a necessary ingredient of wisdom to the design process. Involvement of the customer in the design process is essential, but in many cases may be inhibiting influences on free discussion and team meetings. Frequent but more formal meetings with the customer may be preferred to a team membership. Okay, just to finish up here, as a summary, first, management system development and risk. System engineering is a part of project management that provides technical guidance, system integration, and technical communication. The program manager, project manager, and system engineer all play key roles in the management, budgeting, and execution of the system. The work breakdown structure, the system engineering role also involves contributing to resource allocation, task definition, and customer interactions. With the initial focus on the development of the WBS, a hierarchical task organization that subdivides total effort into subsequently smaller work elements. This provides a basis for scheduling, cost, and monitoring, and enables cost control and estimating. One key tool used for program scheduling is the critical path method, CPM. CPM is based on WBS work elements and creates a network of sequential activities. Analyzing the network enables the system engineer and program manager to identify paths that take the longest to complete. Next, the system engineering plan and the system engineering management plan. The SEP, system engineering plan, often is associated with U.S. government contracts, addresses the program requirements, overall technical approach, and metrics for the program. The SEMP plan implements the implementation of all system engineering tasks. In the process, it defines roles and responsibilities of all participants. And organizations of system engineering. The system engineering organization spans disciplines and participating organization, but also adapts to the company organizational structure. Therefore, system engineering must communicate effectively what, when, and why to their proper stakeholders and provide technical reviews for the participants. In large programs, systems engineering is supported by a system analysis staff. Large programs will require formal system design teams which integrate major subsystems and subcontractors and the products of software systems engineering. These teams contain members from support, engineering, and the test organizations, and typically contain specialty, that is, concurrent engineering members as appropriate. They may also include user representation when appropriate. A key role for system engineering involvement in these design teams is to keep their focus on the success of the entire enterprise. Okay, well, that's going to end it for this chapter. Thank you very much.